Good morning, everyone, or good afternoon, depending on where you are. And thank you for joining me today. My name is Claudio Tortorici, and I'm a senior researcher at the Technology Innovation Institute in Abu Dhabi. And today I'm here to speak about CSIOR, an algorithm for ordered triangular mesh regularization. 3D information can be represented in several ways. We have depth images that aim to represent the depth information using a gray level scale on a standard 2D image. We have cloud of points that are a real 3D mean to represent the 3D information, where all the points are represented by their 3D coordinates. We have the voxels that are the 3D counterpart of the 2D pixel, and we have the mesh manifold that are cloud of points where all the points are connected by polygons. And when these polygons are triangles, we speak about a triangular mesh manifold. Mesh manifolds are very effective to represent surfaces. In fact, they represent very well also the geometric texture. The geometric texture is a corrugation of the surface which locally alter the geometry of the surface without altering the overall shape of the object. However, mesh manifolds have some disadvantage. In fact, often they have what we call an irregular tessellation. In other words, the triangles, also called facets, that compose the mesh have different size and or shape. Also, neither the vertices or the facets are ordered in any manner. So today I will speak about some state-of-the-art approach, then I will present CSIOR, I will go through its concept and its properties, possible application, and finally to its assessment. So the first approach we want to discuss is the geodesic resampling that use geodesic distance to subsample the original mesh manifold to obtain a more regular tessellation starting from the initial set of points on the mesh. Then we have the spline resampling, which use projection and density function to regularize the tessellation of the mesh manifold. However, as you can see here, it often loses the geometric texture information. And last, we have the project resampling. That is something that we used in the past and resulted to be very effective for quasi-planar surfaces. In fact, it used a projection, and then we regularize the tessellation using the Illinois triangulation, and then we reproject back the points in the 3D space. However, this approach has some limitation when we deal with the complex shape. In fact, it may generate some artifacts on the tessellation of the mesh. So today I'm here to speak about CSIOR, which stands for Circle Surface Intersection Ordered Resampling. This is a two-step iterative algorithm which generates a quasi-equilateral triangular mesh manifold. It also preserves the 3D information, in other words, the object shape and the surface corrugation, and provides a mesh that is globally ordered. It is based on the concept of hexagon propagation. So starting from an ordered hexagon, we can extend the hexagon shape to subsequent rings. And since the initial hexagon is ordered, we can also propagate the order of this hexagon to the subsequent ring. Also, we demonstrated that the number of facets at each ring follow this arithmetic progression. But let's see how the algorithm works. We have two steps, as I said. The first step aims to, it's called circle surface intersection, and it's crucial to maintain the 3D information. So we define a circle which is centered on the midpoint of an edge of a facet that relies on the outer hexagon ring. In this case is the initial hexagon. So it is centered on the midpoint and has as normal to the circle plane the edge itself. Using simple algebra, we can detect this point here, that is the exact intersection of the circle with the original mesh surface. Please note that this point is not part of the original mesh surface. Once the point is detected, we can connect it with a new facets. And then we go to the next edge of the hexagon, and we generate a new ring, we find the intersection and generate the new facet. And we continue so on and so forth until we expanded all the outer edges of the hexagon. At the end of the first step, we have a set of what we call facet out. We call this facet out because they are going outward with respect to the initial seed point. The step 2 instead is important to connect the facet out using what we call facet in, because they are looking inward with respect to the seed point, and is crucial to preserve the hexagon ring progression formula that I showed before, and also to maintain the mesh ordering. When you concatenate facet in and facet out at the end of each iteration, we obtain what we call an hexagon ring that, as I said, it also maintains the order that we had at the previous ring. But let's look to the properties and application of this algorithm. As I said, it provides an ordered mesh, but also this order continues over the mesh, the original mesh boundaries, and also it works in the non-trivial case of non-convex shape. As you can see here in the image, the order continues also in this particular situation. Also, we say that the hexagon ring provide an isogeodesic approximation. In fact, on the left, you can see the isogeodesic contours starting from the tip of the nose, and here the hexagon rings starting from the same point. They approximate the behavior of the isogeodesic contours. Also, the algorithm provides the facets normal coherency. In fact, often we have a mesh manifold where the facets are not coherently oriented, and this requires some kind of pre-processing before to use descriptors that rely on the normals of the vertices or the facets of the mesh, while with this algorithm we already provide not just a mesh that is ordered and homogeneous, as we will see later on, but also with all the facets coherently oriented. One possible application of our algorithm is the raw face resampling and cropping. In fact, when you have a raw face scan, it's quite easy to detect the tip of the nose. Starting from that point, we can resample using CSIOR and thus obtaining a mesh that is regular, but also since the facets are ordered, therefore also the ring are ordered, we can select n number of ring using certain criteria and crop the image with no additional cost for the detection of the face. Also, since the ordering structure follow a polar fashion, we can extract polar grid from the mesh, and we will see how this can be useful in a minute. Also, we noticed that the order at each ring follow a certain scheme, and using this scheme, we are able to detect an image-like grid that can be used to export the information from the 3D space to the 2D. And this is what this slide is about. So as you can see, from the mesh manifold that you see here on the left, we can generate some geometric information. We can extract some geometric information from the mesh. In this case, we have 3 different curvatures. And in the case of the polar grid, we can use a simple polar to Cartesian transformation to generate an image that carry the 3D information that we extracted directly on the mesh. Instead, for the image-like grid, we don't even need any kind of transformation. It's as it is already an image-like grid, like the image, the grid of pixel of the image. Also, we can combine 3 different descriptors in an RGB image that carries all the geometric information that we desire to carry and export to the domain. But let's go to the assessment of our algorithm. CSIOR has been assessed against the 3 state-of-the-art approach that I presented before in terms of tessellation quality and geometric texture preservation. For the tessellation quality, we used the edge length ratio, the facet area ratio, and the ring propagation regularity. This latest one, it compares the regularity of the position of the ring with respect to a nominal ideal case. And in this case, the lower the value, the better. And as you can see, the CSIOR outperforms the other approach, and of course the original with respect to the edge length ratio and the facet area ratio, but it slightly underperforms in terms of progression regularity with respect to the spine resampling. However, as we will see in a minute, this will be at the expense of the geometric texture preservation. Another way to look to the tessellation quality is the distribution of angles of the triangle facets on the mesh. And as you can see from the image here, from the graph here, with CSIOR, we have a peak at 60 degrees. It means that almost all the facets are equilateral or quasi-equilateral triangles. For what regards the geometric texture preservation, this is a not trivial analysis, but we decided to analyze the Hausdorff distance and the ICIP error. For the Hausdorff distance, as you can see, we outperform sensibly the other state-of-the-art approach. However, we underperform with respect with the ICIP error with respect to the geodesic resampling. But remember that this approach is, these results is justified by the fact that the new mesh generated by the geodesic resampling is a subsample, a subset of the original mesh manifold that justify the smaller ICIP error. So in conclusion, I presented CSIOR, which stands for Circle Surface Intersection Ordered Resampling, which is capable of producing quasi-equilateral triangular mesh manifold, also to preserve the 3D shape and geometric texture information. And to the best of our knowledge, this is the first resampling algorithm that encompasses global ordering. Also, as you can see from the images here, CSIOR is the approach that provides the best trade-off between tessellation quality and texture, geometric texture preservation. With this, I conclude, and I would like to thank you for your attention. Please do not hesitate to contact me to my email if you have any question about our work. Thank you very much and stay safe.